कुछ समझ आ रही कुछ सही हो रहा है कुछ? All right, so today we will motivate the existence for energy bands in crystalline matter. And we're talking about energy bands for electrons. So far we've looked at the free electrons. These electrons, to first approximation, do not interact with anything. They just see this positive potential created by the positive ionic cores. There's only one instance that we've seen for interaction, and that is electron-phonon interaction, which causes relaxation, which causes a finite thermal conductivity for the electrons and a finite electrical conductivity for the electrons, because this resistivity occurs due to scattering of electrons by phonons. In the last lecture, at the very end, we also started looking at the electron-electron interactions, how electrons interact with other electrons, and this is an effect that only dominates at small temperatures. Now, if you have this free particle wave function, which is just a plane wave, and you do not have any impurities and you do not have any phonons, you are at room temperature, at absolute zero as well. Still, the electron is seeing a periodic potential due to the ions. So we would like to now break this assumption that the electrons see a homogeneous positive background charge. Now they are seeing a periodic potential. So if you have a string of atoms inside a solid, I'm just showing this in 1D for convenience, then on the site of each atom there has to be some potential for the electrons. So if you just imagine that this is a potential similar to hydrogen atom, it's a potential well. So the potential for hydrogen atom is like a well. It has a 1/r dependence, where r is the distance from the nucleus. So there is a periodic potential, and we're not concerned with the form of that potential, but nevertheless there is a periodic potential because of the periodic arrangement of the atoms inside the crystal. So if this lattice spacing is A, then the periodicity of the periodic potential would be given by V, would be given by VR, and the periodicity is imposed by this condition VR plus capital R, where R is a shorthand for Na plus N2B plus N3C, where A, B and C are unit vectors or unit cell vectors, translation vectors. So this potential has to be periodic, and this exists even at 0 Kelvin. So the electron wave that is supposedly or purportedly passing through this crystal is seeing a periodic potential. Now, whenever you have a periodic potential of this kind, it's a periodic function, so it can be expressed as a Fourier series. So this function VR can be expressed as some Fourier coefficient. Let's call it Vk. Now k is a vector in the reciprocal space. E raised to power I k dot r, and you take the sum over all k's inside the reciprocal space. So you can express the potential in terms of these Fourier coefficients, where each of these Fourier coefficients, so this is the Fourier series which is valid for a periodic potential, and there's a constraint on this k that I'm going to mention in a minute. This coefficient Vk is the Fourier transform of the potential in real space. So the Fourier transform of this potential is VR E minus I K dot with R sum over all of space, and you want to put in some normalization factor as well. I'm calling that normalization factor L cube, where L cube is the total volume of the solid. I'm not using V for the volume because V is now reserved for the potential. So this is the Fourier transform of the potential, and that Fourier transform appears as a coefficient in the Fourier decomposition of VR. So both of these are inverses of one another. Okay, so these are important mathematical relationships from Fourier theory that we would like to remember. Now what we would like to do is we would like to see if you do not have any periodic potential, the Hamiltonian for the system is simply p square over 2m, and the eigenenergies are given by h bar square k square over 2m, and the wave functions, they are simply given by the proportional to E I k dot r, correct? So this is just a free particle in the absence of a periodic potential. This is what we mean by free electrons. And if you plot the dispersion relationship, this dispersion relationship k and Ek, it is a parabolic curve. So far so good. There's no problem about this. So this is a quick recap of free electrons, and this is the impact of a periodic potential. Now we would like to see what is the impact of the periodic potential, how would this, for example, change, and so on. The periodic potential will now appear in the overall Hamiltonian for the system. So the overall Hamiltonian will now be p square over 2m plus our VR. I'm going to put a hat on top of this potential. Now I also assume that for free electrons, this state, this is a wave function in the position space. So this is identified by, you can also write states in the momentum space. So I can write this state in the momentum state through a ket. Let's call that ket k. So for a free particle, I can have the quantum state ket k, which when expressed in the position basis is given by E I k dot r, and I can put in some normalization factor if I like. Okay, so this is a free particle. This is the wave function for a free particle. Okay, and it's identified by the unit vector, by the momentum vector k. Likewise, I will also have for another free particle of momentum k prime when expressed in momentum space, in position space, it's going to be E I k prime dot r. Okay. Now what I would like to do, I would like to solve the Schrodinger equation in the presence of a periodic potential VR, where VR has this property. Okay, that's what I would like to do. So I would like to see how do electrons behave in the presence of periodic potentials. All right. So one important aspect that you might recall is that if you look at the decomposition of the Fourier series for VR that I've written at the top, if V is to be periodic, there are certain constraints on K. So if I replace R by R plus capital R, where R is a translation vector in the real space, I will get K P K E I K dot R small r and then E I K dotted with capital R term. But if this has to be equal to VR, then it simply means that this term has to be equal to 1. Correct? So when is this equal to 1? When k is so when k is 0, okay, that's one possibility. That's the only possibility.
Multiples of 2 pi.
2 pi? Why? Because, why? There has to be, this is first of all dimensionless. So what should k be if this is to be 1? Of course this phase has to be some multiple of 2 pi. But what kind of k should we have so that this is a multiple of 2 pi? So what is that thing called?
Reciprocal.
So k must be a reciprocal lattice vector. So k must be, this is periodic only when k is some h a star plus k b star plus l c star, or some reciprocal lattice vector hkl, correct? Only in that condition will k dot r be equal to k dot g will be some multiple of 2 pi, correct? So for periodic functions, remember that Vr is given by V reciprocal lattice vector. The Fourier coefficient in K space is sampled at the reciprocal lattice points E I G dot R. So this is a subtlety about the periodic functions. Okay, so this is, all of this is preparation. So now let's see if I were to let's look at this expression. So the goal, what is our goal? Our goal is, now we have a periodic potential. We would like to see how does this dispersion relationship change. That's the goal. That's the motivation. Okay, फ्री इलेक्ट्रॉन्स पहले थे, लेकिन अब उसके ऊपर पीरियोडिक पोटेंशियल आ गया है, तो अब हम देखना चाह रहे हैं कि फ्री इलेक्ट्रॉन वो फ्री रहते हैं कि नहीं. ठीक है, दे विल बी ऑलमोस्ट फ्री इलेक्ट्रॉन्स, बट there will be a departure from this this kind of behavior. So let's look at the blue equation that I've written. So if I replace k by, so I'm just going to do a little bit of algebraic fiddling, some algebraic acrobatics, nothing else. So I replace k by k minus k prime. This becomes 1 over L cube d cube r v r e minus I k minus k prime dotted with r. Okay. On the other hand, I do know that if I would like to invoke quantum mechanics into this, I would like to see that this coefficient is really a matrix element in a Hamiltonian. So let me assume that I have this potential Hamiltonian function v hat, and I sandwich this between bra k and cat k prime. Let's form this matrix element. So what I could do is this matrix element would be K ket R bra R V, which is a function of R ket K prime summed over R's. Correct? Now this is a function only of R, so I can move this bra to the right. This becomes d cube R. This is just a scalar function. This term K prime R has been defined over here. So I will get 1 over L cube E plus I K prime, or minus I K minus K prime dotted with R. But this is equal to this coefficient as well. So this coefficient here is equal to a matrix element. Got it? नहीं दो दफा है ना. So this is a matrix. It's a Hamiltonian matrix, and these are elements inside that matrix. Okay. Now what we would like to see is that another subtlety. Another subtlety is that if this matrix element vanishes most of the times, only in a certain case it doesn't. And that is going to connect this idea to the whole idea of diffraction theory. So if I were to take this expression, this is over all of space, integral over all of space, correct? But what I could do, since it's a periodic function, if I have this term here, Vk minus Vk prime, I could do a trick. I could replace this d cube, this r. So what I could do, I could replace this r by some location x inside a unit cell. X is some location inside a unit cell plus translation vectors, all translation vectors possible. So since the unit cell is a repetitive unit, I can just integrate over all the points inside a unit cell and then translate with all possible translation vectors. I'll generate the entire integral over all of space. So what I could do is I could write this d cube r as dx, integrate, and this is only over a unit cell. Vr becomes now Vx, this is d cube x, Vx plus capital R e raised to power minus I k minus k prime dotted with small r, small x plus capital R. And I need to sum up over all possible r's inside the system, all possible translation vectors. So I need to sum this up over all r's, capital R's. Yes. कौन सा R? No, R is just some position vector. This is some position vector and we're taking integral over all of space. So what we are doing is that we have a unit cell. Our solid is broken down into many unit cells. Okay? So I just integrate over a single unit cell. So that is this integral. So x belongs to the space inside a unit cell. And small r, but since I need to cover all of space, I take an integral over all the contents of the unit cell, and for each point I translate over all possible lengths, all possible unit translation vectors, capital R, where capital R is given by what I've written over there. I will generate the entire structure of this of space. इस डायग्राम में नहीं है. Small r has now been replaced by x plus capital R. Small r तो शुरू में कोई भी पोजीशन थी ना स्पेस में. नहीं तो वो तो पहले ही वो सारी स्पेस को कवर कर रहा है. Small r is now initially small r spanned over all of space. Now we have broken down this into smaller parts. We find out the structure factor or the factor over just one unit cell and translate it throughout the periodic array of unit cells. Because I want to prove a point. So if you look at this expression over here, this expression, however, since the system is periodic, I will be left with Vx. So the entire integral V k minus k prime will be 1 over L cube sum over capital R E minus I k minus k prime. I can take this thing out of the integral, right? Put this in a bracket of its own. D cube x Vx E minus I k minus k prime plotted with x. This is over a unit cell. Now these r's, now this is some fixed vector. Some fixed vector here. There is no integration over k prime. This is just some fixed k minus k prime. But this r can be anything. It could be, it encompasses all positive and negative translation vectors. And all of them. So that the entire space is filled. So this integral is always 0. Only under the condition that this term turns out to be 1, which means that this factor is a multiple of 2 pi. Only then would this term not be equal to 0. So this is something we've already seen. So we do know that this term has to be some multiple of the reciprocal lattice vector. Otherwise, the coefficient will turn out to be 0. So k minus k prime has to be equal. So the resolution to this thing equals L cube Kronecker delta k minus k prime comma g. Okay. So this means that this term is non-zero only when k minus k prime is g. And what is this relationship? K minus k prime is g. Plus, could be plus g or minus g, doesn't matter. So have you seen this relationship before? K prime equals k plus g. You've seen this relationship before in diffraction studies. The change in the propagation vector for X-rays along a scattering direction must be equal to a reciprocal lattice vector. So X-rays can scatter. Here electrons are being scattered by the diffraction grating that is set up by the periodic arrangement of the crystals. Okay, so this is exactly the Bragg condition that we've derived for diffraction, identical to this. So when we have a periodic arrangement of atoms inside a crystal, the problem is totally analogous to the scattering of X-rays from periodic arrangement of electron clouds. Here we now have an electron wave which is being scattered by the periodic arrangement of the atoms inside the crystal. So this was an A side and a subtlety, but now we have a formula for calculating this matrix element. And why do we need this matrix element? What is your guess on how we could calculate the new energy? Once we know certain properties of this periodic potential, we know the unperturbed energy states, how do you think we can calculate the new energies in the presence of the periodic potential? What tools do we have at our disposal? What does a basic course in quantum mechanics offer to help? Yeah? Interaction Hamiltonian. Yeah, so one kind of interaction Hamiltonian is the time independent perturbation theory. So we can apply the time independent perturbation theory. We now know what the perturbation is. This is the perturbation. So the new energies in the presence of this periodic potential. So we're going to treat this problem now in light of perturbation theory. Time independent perturbation theory. So the energy in the presence of a periodic potential is the unperturbed energy, E, let's call it E naught. Energy of course depends upon K. That's what the dispersion relationship means. So unperturbed energy E naught, which is just the parabolic function plus extra terms. So the first order correction, what's the first order correction in this energy according to the time independent perturbation theory? पहले कहीं नहीं किया हमने इस कोर्स में, Q2 की भी एक कॉपी है आपकी. Okay, so the first order perturbation term क्या है देखो. That's the second order term. So the first order term is simply the perturbation, and you want to find sandwich it between the state for which you would like to measure the change in energy. This is the first order perturbation term. The second order perturbation term is V K K prime modulus squared E naught K prime minus E naught K, and you sum over all K primes which are not equal to K. Okay, so these are the first and the second order correction terms. So this we already know is h bar square K square over 2m. Now what about this term? If I look at the integral that I've written multiple times, let's look at this integral. So I'm going to sandwich this Hamiltonian in between two identical states. So if I sandwich it between two identical states, this is K, this is also K, this term turns out to be e raised power 0, this is 1. So this is just a sum of the overall potential. That's going to be some constant. There is no spatial variation in that. It's going to give you the average potential. But that's what we've done for free electrons anyway. Average energies or constant energies they can't be measured, and you're going to put that average to be 0 as well. Okay, datum level, it's a datum level for the energy. So this term is some constant, let's call it V naught, put it equal to 0. Whereas this term This is h bar square k prime square over 2m. This is h bar square k over 2m. So this is a much larger term as compared to this term, and this term is, by the way, k prime has to be equal to k plus g for the numerator to be non-zero, because this is something we've already seen. But this term is going to give you a very small correction. The second order correction is going to be very small, okay, because the denominator is so large, correct? So the point is that there is very little disturbance to the potential according to this prescription. However, there is a problem. The problem arises when both of these terms become equal, because then you cannot apply this non-degenerate perturbation theory. Do these energies become equal at some point? So the answer lies here. They become equal at, if k prime equals k plus g and we are at a zone boundary, do these energies become equal? So if I draw the dispersion relationship again, k this is E. Suppose I am focusing on one dimension at the moment. This is pi over A, and this term, this position is minus pi over A. Let me now, I'll have to zoom in, sorry. Pi over A, this is minus pi over A. Now these are boundaries of the first Brillouin zone. So this separation here from this point to this point is 2 pi over A. It's equal to 1 reciprocal lattice vector. And we do recognize that because it's a symmetric function of k, it's a parabola, it's a symmetric function of k, the value of energy is going to be the same at these 2 points. And we only need to consider points that are separated by the translation vector. So likewise, there will be another, so at 2 pi over A and minus 2 pi over A, there will be 2 points once again, which are the boundary of the next Brillouin zone, or which are points which are separated by 2 times g. So, but at these points you cannot apply the non-degenerate perturbation theory, because at these points the energies are equal. So in order to find out, this term is always 0. So this term becomes prominent when the denominator has 2 similar energies, and at these locations you cannot apply the normal non-degenerate perturbation theory, you have to apply the degenerate perturbation theory. Right? So let's apply the degenerate perturbation theory. Everything is systematic. There is no kind of big physics here. It's really nice, simple physics at work. And the results are, in fact, they are universal, they are ubiquitous, they really are of civilizational importance, because these results tell us what are metals, what are conductors, what are insulators, how does electricity flow. All the different classes of materials, crystalline materials, stem out from this simple application of energy bands, as we'll derive in a minute. So how do we apply degenerate perturbation theory? What should we do? So what's the recipe for the degenerate perturbation theory? क्या करेंगे? PhD students बताएं. Dirac series वो क्या होती है? Alright, so what we could do is we could express the Hamiltonian in terms of in a basis which is defined by the eigenstates of the unperturbed Hamiltonian, which means that we can write down terms of this kind: h k prime, h k, h etc. Right? So let's write down the Hamiltonian in a basis, and the basis is offered by the eigenstates of the unperturbed Hamiltonian, and those eigenstates are k and k prime. So we write down the Hamiltonian as a 2 by 2 matrix. Consider two states because we're looking at the difference between two wave vectors k and k prime. So at this location, let's write h k k. Here let's write k h k prime h k and k prime h k prime. This Hamiltonian will act on an eigenfunction. So suppose I have a Hamiltonian, it acts on an eigenfunction. Suppose the eigenfunction ket phi, it has to be some superposition of the unperturbed eigenstates, some alpha k plus beta k prime or k plus g, right? So this H must act on phi to give you the energy on phi, okay? Where phi is an eigenstate of the perturbed Hamiltonian, right? So the eigenstates of the perturbed Hamiltonian will be some superposition of the unperturbed eigenstates. They have to, because the unperturbed eigenstates form a basis for this two-dimensional system. Got it? This is basic quantum mechanics. So now we have this Hamiltonian and we can just write down the matrix elements. So what's the first matrix element? Is h bar square k square over 2m. Let me write this for convenience. Let me, instead of writing this entire thing, let me write this E naught k, unperturbed eigenenergy. Okay, what is this term? E naught k prime h bar square k prime square over 2m. What about this term? So h, remember, is a sum of the unperturbed plus the perturbed part. So the sandwich, when you sandwich this, you get 0. Okay, this term will be v k minus k prime. This will just be this term over here, which is vg. Okay, where g is some reciprocal lattice vector. So this is vg. Some Fourier coefficient of the decomposition of the potential. Fourier coefficient determined at a reciprocal lattice vector g. Right? So what about this term? V minus g, because this is k prime, this is k prime minus k, v minus g. Or you could also write v minus g as vg star. And so this term is the complex conjugate of this term, and that's because v is a real function. So this is a Hermitian matrix, and I'll give this as a homework problem as well, just to prove this. Okay, so this is our H. Now how do we find the corrections to the energy? according to the degenerate perturbation theory, what you need to do, you look at this equation, you kind of take H to the other side, and find the determinant of this matrix, put it equal to 0, and you solve this characteristic secular equation as it is called, and solve it for finding out the perturbed energies. That's how you apply the degenerate perturbation theory. So let's try to do this. So this becomes E naught K minus E Vg star E naught K prime minus E determinant. This must be equal to 0. And by the way, this description is only applicable at the zone boundaries, right? We're only talking about the zone boundaries. This perturbation is happening at the zone boundaries only, at or near the zone boundaries, at or really close to the zone boundaries, the boundaries of the Brillouin zones. So this is trivial to solve. So the solution to this, E naught K minus E squared equals Vg modulus squared. So G is, if you have G here, this is at the first edges of the first Brillouin zone, otherwise you'll have 2G, 3G at the other zone edges. So this means that my energy, the perturbed energy, will be the unperturbed energy remember that this is the energy at K plus G, which is the same as this energy. Okay, so after perturbation, this would become E naught computed at the zone edge. This is at the zone edge, please keep that in mind, plus minus Vj. So let's see how this plays out. Let's draw a diagram of how these energies change. Okay. Suppose I'm just plotting this in 1D, and you can imagine what would happen in 3D. Okay. So this is K and Ek. So alright, so this is our nice unperturbed energy. Parabolic, right? Alright. Now what's going to happen? Suppose this is 0. This is a point pi over A. This is minus pi over A. These points are separated by 1G. Then you have a point 2 pi over A. And you likewise you have a point here minus 2 pi over A. And these points are separated by 2G. Then you have a point 3 pi over A. Here you would have a point minus 3 pi over A. And these points are separated by 3G. Now let's plot the perturbed dispersion relationship. Now what's going to happen away from these zone boundaries? Everything is going to remain the same. No change. Hardly any change. However, now I'm going to exaggerate a bit. I'm going to exaggerate the drawing a bit. As you approach the zone boundary, this energy now takes up this negative sign. If this were not this term didn't exist, no perturbation, it would keep on following the white curve. But now just before the zone edge, it kind of drops down a little bit because of this minus Vg. Correct? So it starts looking like this, drops down. Okay? Like here it drops down again. As you cross this zone boundary, the dispersion relationship, in normal circumstances, it would have retraced this white path. But now it starts from higher above because there's positive sign. So it kind of goes like this. It then keeps on following this route and then drops down again, drops down again. So this is what is happening here. And we observe that at the zone boundaries, the dispersion relationship has, as if someone has taken a scissors and cut it out. There are no energy levels. All of these are energy levels. Everything is discretized because of the periodic boundary conditions. These are fine points in the K space. Each point has a separation 2 pi over L. So, but there are no energy levels in this region. And this gap here, what's the amount of this gap? It's 2 times Vg modulus. What is this gap? This gap is 2 times V 2G modulus. So at the zone boundaries, we see these gaps in the energy levels. There are no energy levels that take up any position in the region that I show in green. No energy levels here in this region. These are called band gaps. This is one band, this is the next band. So in between bands, so the entire dispersion relationship is now punctured. It has been cut very neatly at the zone boundaries into bands of varying heights. So there's another band over here. Sorry, another gap over here. There will be another gap over here. These are called energy bands. And this is how the band structure is formed inside a solid with a periodic crystal. Okay, let's take a 2-minute break. This kind of diagram shows the dispersion relationship in the extended zone scheme. It's called the extended zone diagram. So, but we do know that the dispersion relationship, when expressed in the K space, the reciprocal space, is periodic with a translation period of G. So whenever I take any string and move it by plus G or minus G, it's going to be the same. So this string, I can move it over here. I can move it backward by minus G. This I can move forward by plus G. This I can move backward by 2G. This by plus 2G. And I can draw a new scheme, which is equivalent to this scheme, which is called the reduced zone scheme. Okay. So if I were to draw this diagram in the reduced zone scheme, So everything is then drawn inside the first Brillouin zone. Okay. This is one branch of the dispersion disk shape. It's called a band. One band. It must be labeled by an index J, say J equals 1 for this band. Then I move this backward by minus G, this forward by plus G. It's okay if I do that because it's a periodic function of period G. So when I do that, I get this second band. And there's this gap between bands. And if I now repeat it for this third band, I'll get this. If there were no perturbation, there will be no energy bands in this reduced zone scheme. They will be touching, these points will be touching, and this graph will look like this. Right? But now there are these bands that have opened up. These gaps that have opened up. So this is, let's call it the J equals 1 band. Let's characterize this by J equals 2. Let's characterize this by J equals 3. So the entire energy level structure has been split up into bands, separated by energy gaps. I can also draw another scheme which is called this is the extended zone scheme, reduced zone scheme. I can also now repeat this overall space and get the repeated zone scheme. The energy band diagram. This is complete. This shows everything inside the first Brillouin zone, and this shows it in the extended sense. Okay? Now just imagine the beauty of this all. Let's focus our attention back onto this reduced zone scheme. Let's talk a little bit about conduction, about the classes of materials. Any questions? So now we have a good motivation of why these bands are formed and what are the energy gaps and how big are they. And those energy gaps are not of the same size, they could be of different sizes. Because one is Vg, one is V2g, one is V3g, and so on. Now if I have a band like this and the next band like this, suppose now this is the first Brillouin zone, correct? First Brillouin zone. In 1D this is pi by a, this is minus pi by a. So what's because of the periodic boundary conditions that you already know, you can apply the Born, von Karman conditions, periodic boundary conditions. You know that this band is really composed of finely spaced k points. So what's the separation between two k points? What's the separation? Delta k. Isn't it 2 pi over L, where L is the total length in one dimension, so which is 2 pi number, let's call the number of unit cell NC into the lattice spacing. So this is the separation between any two of these points, delta k. So what's the total number of points inside the first Brillouin zone? So the number of k points inside the first Brillouin zone is 2 pi over A divided by delta K. So the number of points inside this band is the number of unit cells along the length. Now each K point, remember, can hold 2 electrons. Now if there is one free electron in one unit cell, this band will be half filled. And it, by the way, it also depends upon the density of states. Right? So just assume we're just ignoring that, but this band can be filled partially, completely, depending upon how many free electrons are available inside this band. Correct? So if I have a band, and remember, this is always true. This formula is really important. The volume of the first Brillouin zone, which is of course a volume in the K space, is also the volume of the Wigner site cell. So if you take this volume and divide by the volume of each point in K space, let's call it Vk, which in my case, in one day I call it delta K. This must equal the number of unit cells inside the three-dimensional solid, which could be n1 into n2 into n3, where each one of these is the number of unit cells along each dimension. So this is an important formula. This is what's the size or volume, what's the retention capacity of the first Brillouin zone. So in a band, so many states will be available, so many K points will be available, so many K points will be available, and each K point can harbor 2 electrons. Okay, so now we have a density of electrons, a number of electrons, and they occupy this band and do it successively. And so what you could have is, you could have a band that is partially filled. Correct? So for example, if you have, we'll talk more about this in the next lecture, which is going to be our last lecture on Tuesday, ungraded. I think we need to finish off this idea. The idea is important, not the exam. So we are ignoring the complexities of the shape of the Fermi sphere and the density of states for the time being. But suppose this band is half filled. Blue shows the occupancy of electrons. If I apply an electric field, this is Kx. So I apply an electric field along the minus x direction. What's going to happen to these electrons? They're going to increase their K in the positive value in their direction. So now empty states are available here, right? So this entire string of electrons, like the beads of a rosary, they will just kind of slip and increase their K values. So there will be some kind of population difference, more electrons with positive Kx than with negative Kx, which causes electrical conduction. This is the kick in the momentum that these electrons will find. So this presence of available electron states inside the band renders this material into special class. What is that material called? Huh? Bolo bolo. Kya? It's a conductor. This is a metallic conductor. So this band is half filled, it's a metallic conductor. If this band is completely filled, then there's a gap between this band and the next band. So this is a conductor. So if I have this band and another band, and now there's a gap. This is completely filled. It might happen for divalent metals. So now if you apply an electric field, the electrons, unless they have enough energy to overcome this energy gap, they will not be able to conduct. They have nowhere to go. Unless you do some kind of breakdown experiment, you apply such a strong electric field that the electrons can be excited to the upper band. Or you do thermionic emission. Or you do field emission, or something of this kind. Normal conduction cannot render this into a conducting material. So if this gap is large, generally more than 1 or 2 electron volts, it's called an insulator. Otherwise, if the gap is small, it's called a semiconductor. You could also have, so in this case, the Fermi energy is right at the edge of the band, EF. Here, the Fermi energy is inside a band. So this is the metallic conductor. You could also have scenarios in which this is the Fermi energy and there are 2 bands. So these bands are filled up to the Fermi energy. Both of them are filled. So they will form a conductor. So there are different kinds of possibilities of where the Fermi sphere ends, where the Fermi surface ends, and where the bands are. Now I think it's really the right time to talk a little bit about effective mass for the electrons. By the way, one thing I would encourage you to do as a homework. So this is the calculation right at the gap. What if we kind of remain close to the gap, but not at the gap, close to the gap? So instead of being at n pi over a, suppose we are at n pi over a plus delta. So the secular equation will become E naught n pi a over delta plus Vg star E naught computed at minus n pi over a plus delta, where delta is a small number. So now what you would like to do, you would like to find out the roots of this equation, okay? And so you can actually find out a functional form for what this energy dispersion regime looks like in this region. It's going to be a parabolic function of delta. So you can find out what the form is over here, right? This will have some mathematical form as well. Okay, so you can use this secular equation to find out this form. By the way, we've talked about the eigen energies for this perturbation. What about the eigenstates? The eigenstates will also be determined through this equation, right? So once you have the eigenenergy, you can solve for the eigenfunctions as well. I'll give this as a homework, okay? So all of this is examinable, by the way. Not Tuesday's lecture, but everything up till today is examinable. Now let's spend some quality time on the effective mass. The idea of the effective mass of the electron. I do know that if I have a particle such as an electron inside a solid, and the particles are seldom plane waves, they are mostly these pulses or wave packets, and the wave packet moves with a characteristic speed called the group velocity, and the group velocity of a wave packet is given by d omega by dk. Okay, so let's keep this in mind. So if an electron is moving inside the solid, it can be modeled as a wave packet instead of a plane wave. Wave packets are better models to particulate transport. Okay, and this wave packet can be Fourier decomposed as a sum of plane waves. This is something you learn in your first course on quantum mechanics. देखा है वरना ही? Wave packets नहीं देखे हुए quantum mechanics में. So this is the group velocity. Okay, so far so good. Now we know that there is a dispersion relationship. So this omega is really E over h bar. So 1 over h bar dE over dk. Okay. So what is dE over dk? Now we have a band. The band has a certain dispersion relationship. What is dE over dk for the band? It's the slope of the band. It's not zero. I mean, could be anything. It's the slope here is a straight line, and then it kind of goes down to zero. So it's some property of the band. So the group velocity of the electron becomes some property of the band, and it becomes a function of k. What is the k value, right? Because of dispersion. Now if this is true, let's talk about mass for the electron. The electron will have some mass, some effective mass. If I take the derivative of this group velocity, I will get some acceleration, some quantity which may not be the physical acceleration of the electron, but still some quantity that is proportional to acceleration. So this becomes 1 over h bar d square e dt dk. Correct? So I just apply the chain rule or the product rule or whatever it is called, d square e dk square dk by dt. Now what is dk by dt? Remember h bar k is some momentum. So if I take this, if I make this, so let's call this some a, something that has the dimensions of acceleration. So a equals 1 over h bar square d square e dk square. So this is the derivative of momentum dp by dt, which is some force. So first of all, so dimensionally this term here is the inverse of mass. The inverse, this mass is called the effective mass for electrons, and it's a purely shear property of the band, in particular the curvature of the band, the bending of the band, which is called curvature, right?
Just to clarify, effective mass को inverse of mass करेंगे और करेंगे inverse of effective mass.
This is the inverse of effective mass. Okay, so let's plot this. K E. Let's plot this for a one-dimensional case. This is our pi over A. This is the boundary of the first Boulogne zone. I have a parabolic relationship, but at the zone boundary, this curve flattens out. If I were to plot dA by dE by dK for this band structure, what will it look like? Here it's positive, keeps on going positive, then it turns around and goes to 0. And then after this, it starts off at 0 and recovers its positive slope. This is dE by dK. This is just the gradient of this curve. Correct? Now what I would like to do, I would like to find out the derivative, this thing, d square E, the curvature of the original band, which means I would like to take the slope of this curve again. So I'm plotting the curvature of the band. So positive, it's positive, right? Then it turns negative and just finishes off at some negative value. Then it immediately becomes positive. And then it plateaus off at the same value. So remember, here this curve is positive, it becomes negative. It's positive all the way here. So what does this tell us? This really tells us, if I were to take the inverse of this graph, I will get the effective mass. Now, in all of this region, away from the zone boundary, the effective mass is just the real mass of the electron. You can find that out. You can just plug in the values. You can plug in the values for E, h bar squared, k squared over 2m. You'll find out that it's just the real mass of the electron, the inertial mass of the electron. But it starts to change over here. And close to the zone boundary, it can even become negative. The effective mass of the electron at the zone boundary becomes negative. So if you have an electron wave with this k, which is close to the zone boundary, you will get a negative mass for a negative effective mass for the electron. And you can also, what does it physically mean? So you can think of this as, and it's real. So if you do a thought experiment in which you have a foil, you apply an electric field. Now what the electric field does, so if you have an electron over here, it's a conductor, an electric field can shove the electron towards the zone boundary. It can move the electron up on this band if empty states are available. So when the electron reaches this zone band, its mass becomes negative. So what that means is that if you have a spray of electrons coming in, K1, inside this metal, and you keep on increasing the electric field, now what is happening to the electron inside this metal is, under the action of this electric field, it is accelerating like a normal charge, right, of some mass. But all of a sudden, as it approaches, its electric field goes up, the K goes up, it approaches the zone boundary, its mass becomes negative. When its mass becomes negative, for the same force, the acceleration will change sign. And when this happens, the wave vector for the electron is going to change its direction. So the electrons will now be scattered or reflected from this foil. So this is a kind of thought experiment. So sometimes conduction is a response to, is a response to a stimulus. The stimulus is the forced electric field. So depending upon the conduction velocity is a measure of the effective mass for the electrons. Right? So this is how the effective mass plays out. It, in the vicinity of the zone boundary, it can even be negative. Now, let's look at another band structure, a complementary band structure. Okay. Once again, I draw a band structure. This is my zone boundary. Suppose this is my band structure. This is a large gap. This is a large gap. It's possible. And this large gap really means a large 2Vg, which means a large potential, which really means that the electron sticks to the ionic core. It's tightly bound to the ionic core. So this is generally called the tight binding model. So you can have a large band gap, no worries about it. Now if you look at the curves for the slope for this band gap, so this is a much smaller slope, and a small gentle kind of depression, correct? Isn't it? It's a gentle depression. And if I look at the curvature of this band, everything is very gentle here. It's a very small curvature, right? You just take the derivative of this again, it kind of slightly changes. Now the mass here for the electron will be much bigger than this mass, because the reciprocal of this curvature is much large. So this is an example of a wide band gap material. Wide band gap. And for a wide band gap material, in which this gap is much larger than this width of the band, or the band width, if this gap Eg is much larger than the band width, or the width of this band, it's called a wide band gap material. So for the wide band gap material, the mass of the fermions, of the electrons, can be very large. So this is a heavy electron system, or a heavy fermionic system. And the same kind of argument applies to holes as well. You can have light holes, heavy holes. So this is the concept of the effective mass of an electron as it plays out in condensed matter physics. So on Tuesday, which is going to be our last class inshallah, what I'm going to do is I'm going to give some practical applications of all of this. And there's one theorem that we need to cover, which is called the Bloch theorem. Alright, तो आज के बारे में कुछ सवाल और